beginning. Amazing. Thanks everybody for being here. We're gonna start the biodesign and fabrication workshop. In this workshop, we're gonna show you some computational design tools to produce biologically inspired and informed structures, and also some parametric modeling concepts for the production of toolpaths for digital fabrication. This is, well, as you all know, this is a 3-day workshop. We're gonna do 3.5 hours roughly each day. This is where we're gonna use some tools like Houdini, Grasshopper, Autodesk CFD. This is not necessarily a workshop on each one of these tools. We're not gonna go in depth into each of them. We're just gonna use them as an excuse to introduce these biodesign concepts and ethos. We have tried to structure it so it can be interesting for everybody, regardless if you already know how to use parametric design and modeling tools, or if you're a complete newcomer to these things. We are presuming that most of you guys have at least a little bit of knowledge in 3D modeling. But if at any point you want to ask a question, just throw it in the chat or maybe raise your hand, and we're gonna try to answer any question that you guys might have. So I think most of you guys knew that Dana and I were leading this workshop, but I also want to introduce Edward. Edward is a graduate from the Biodesign Masters as well. He's going to introduce himself in a couple of minutes. We decided to include him as a tutor because he was instrumental to the conception of this workshop, and also because of the large number of participants that we have. So thanks again to Edward for helping us. He's going to introduce himself now.
Hey guys, so I came from a pretty pure architectural background. During my time in undergrad in Florida, I have been mic drop. During my time in Florida, I have been an architect licensed. So in my undergrad, it was a typical architectural program, but I seem to always have this inculcation, like I wanted to always do.
Well, I think he froze. He told us this might happen. Dana, do you want to go ahead with your introduction?
Yes, so we wanted to, hi everyone, my name is Dana. We wanted to introduce ourselves just to show that we came from different career paths, and maybe perhaps like inspire you also to follow biodesign journey. So my name is Dana Mozhigit. I'm originally from Kazakhstan and currently living also in Kazakhstan. We all met
some sort of
at, oh, Ed is back.
Yeah, we're gonna go with Dana for a second here. We're gonna go back to you.
Mm-hmm.
Please continue, Dana.
Okay, yeah, so my career journey was very interesting. I actually studied design, and I worked in graphic design world, publishing magazines like Cosmopolitan, as you see in this image, when I was 22, I think. And then I shifted my career to tech, where we developed lots of applications and websites and platforms for governments, banks, and telecommunication companies in this country and abroad. Yeah, a few years back, I really found my passion in biology. I never thought I can, do something in biology, but actually this program has helped me to understand how to tackle biologically driven design projects and research. So yeah, ever since I changed my path, it's been really great. Currently, I'm teaching at SU University, and also I co-founded Ancient Futures Collective with Hanna Svelbar, a scientist, and we are going to talk about a little bit more in day 2. Yeah, thank you.
Thanks, Dana. We're gonna go back to Ed here.
I just wanted to say that when I was working in the field, I got a lot of architectural knowledge and experience, and it was helpful for the next step in the biodesign because it made me think realistically about how we can create a more environmental future. So as I came into the program, I had a very like deep understanding of architecture, and now that I've graduated, I'm very much interested in material research and kind of how to provide for the new industrial complex something that is more beneficial for environment. That's all.
Amazing, thanks, Ed. Well, my name's Kenneth Wilson. I'm a Peruvian architect. I got my license here in Peru in 2016. At that point, there wasn't really, I would say, any kind of idea around biodesign in the faculty that I was studying at, but I still had a lot of interest in nature-driven design. So my thesis project was a vertical farm. After that, I worked in Mexico City for an architecture studio for 2 years, mostly doing cultural and public space projects. And then I returned to Peru to work with the government for the Ministry of Education. But I guess I just felt like I wanted to go back to design, but not in the way that I had learned it in school. And then I found this biointegrated design masters at UCL, and just the idea of studying in the intersection of biology and architecture just sounded amazing. So I took that on, and that's where I met these beautiful people that you can see leading the workshop with me. And I guess we wanted to share some of these ideas. So we hope that you guys can help us move forward the industry. We have structured the workshop in 3 days. The first day we're gonna go through basically biodesign concepts, introduction to these ideas and this set of ethos. We're gonna do a quick presentation on Edward's thesis project for the BioID program, and we're gonna present the brief for the exercise that you guys are gonna take on. We're gonna separate you in groups of 5, and we're gonna use this exercise as an excuse to learn about these tools and these biodesign concepts. We're not aiming to get, amazing results. This is a very short project, just 3 days. So we're more interested in the process than in the result. Day 2 is going to be about the interaction of these computational design tools, mainly height fields in Houdini, to model mid to large scale bioreceptive structures, so to say. We're also going to introduce some environmental simulation tools in Grasshopper to inform these designs that you guys are going to be producing, also with Autodesk CFD, so we can do some solar radiation and wind flow simulations. And on day 3, we're gonna take a section of these designs that you guys come up with, and we're gonna kind of learn how to produce a toolpath for a robotic arm in this case, but it should be feasible to use this logic for quite a bit of digital manufacturing processes. And on that 3rd day, we're going to have a roundtable discussion so we can see the results of the work that you guys have achieved and kind of have a talk around it. Oh, there we go. Okay, so well, I think Dana can have a lead on this part of the presentation. Dana, can you turn on your mic?
Can you hear me?
Yes, we can hear you now.
Okay, great. So we put together some useful resources for you, starting from lectures by Frontiers of Biodesign. Natsai Chiza, she's the founder of Fabrication. She creates pigments from bacteria, Streptomyces colicolor. And Suzanne Lee, she has amazing work with kombucha. Essentially, it is bacterial cellulose, and a few books on the concepts of biology, how life works. Of course, computational design thinking, because we would like to learn how to think in systems. And we also have to include Braiding Sweetgrass. It's an incredible book on indigenous knowledge and ecological thinking. And the other resources that you can find, it's mainly free, on Introduction to Biology, Biochemistry, and incredible PhD work of Neri Oxman on material-based design computation. Yeah, we will send these links after the workshop. Thank you, Ken.
Amazing. Thanks, Dana. Okay. So, Dan, I think you are also going to take on this part. Hello?
It's okay.
Yeah.
So day one, today, we would like to actually have an interactive conversation about what does it really mean when we say biointegrated design. We would like to introduce our framework and have a conversation with you on the future technologies and its implications in the architectural world. So it's very open-ended. There is no correct or wrong answers. It's more of a conversation and discussion that we would like to start. Yep. Yeah, as you are probably familiar about biomass and anthropomass terms, human-made materials or desynthesized or altered materials now outweigh Earth's entire biomass. And the biomass includes animals, plants, humans, bacteria, and so on. And this is a really critical moment for humanity because this will intervene and have implications in biodiversity, resource management, animals' life, and humans' life, regardless. Ken?
Yes. So, I'm gonna do a quick introduction to our understanding of biomaterials and materials in the construction industry as we know it today. So this is, I want to start talking about an idea, and this is a picture that was shown to us in my undergrad as part of our architectural history course. And this is the Lion's Gate in Greece. And it depicts a couple of lions kind of looking up towards a column. And the true meaning of this piece is still debated. And there's quite a big possibility that this used to depict a deity on top of the column. So it was kind of a religious motif. But the interpretation that our teacher gave us at the moment, and I think it's very representative of the way that some architects tend to or used to think of the construction industry and architecture. And he used to say that in his view, this was a way of this civilization to portray how they had overcome nature, how through their prowess to build, to design and produce buildings, they had gone a step above the beasts. So for some reason, this idea, even though it was a subjective interpretation, it kind of stuck with me. This idea of how we have grown to start thinking that we are somehow above nature, and the things that we produce and the things that we design and we build are of a higher intelligence or of a higher quality. Quite a dangerous idea, I think. And before the way that we build now, there didn't used to be a distinction between biodesign and design and biomaterials and materials. Everything was biodesign and everything was kind of a biomaterial. And each region developed its own very characteristic way of designing and building its own vernacular technologies according to the things that they had close to them. Even with the same material, like in the case of soil construction, you can find very different expressions with the same material because of very particular, very local environmental conditions. So yeah, everything used to be biodesign, so to say. And at some point, late 19th century, early 20th century, the Industrial Revolution starts to push standardization into basically every aspect of our lives, not only products, but also our houses, our buildings, the way that we produce our built environment. And the production and the, so to say, invention of new materials also allowed for new possibilities. Very interesting materials for sure, like cement and steel. And early 20th century, mid 20th century architecture definitely benefited from these new material possibilities and pushed forward not only a standardization in the materials, but also kind of arguably a standardization of styles with this current that eventually became known as the international style, spearheaded by very talented architects like Le Corbusier, Mies van der Rohe, and Frank Lloyd Wright. And this current produced very beautiful buildings, definitely advanced architecture as a career. But the thing is that it is sometimes overlooked that these buildings were not always adapted appropriately to their environment. The Seagram building, for instance, a landmark of New York, is one of the worst performing buildings in terms of energy efficiency. And these ideas, these aesthetic expressions prevail even to this day. This is a building that has been recently opened here in Lima. And we can still see the DNA of this aesthetic current, even though it's also very poorly adapted to the climate here. But going into the materials, concrete, for example, and steel have been widely used in modern architecture. This is the Unité Habitationnelle de Marseille, project by Le Corbusier, a very interesting project in terms of section and how it integrated public spaces into the roof of the building. Steel also took a kind of the forefront in many cases, like this is the Pompidou Center in Paris, also amazing project. But the thing is, these materials, even though they have given us new, very interesting possibilities, have environmental and in some cases even sociological effects that should also be taken into consideration. The production of cement amounts for a big chunk of the CO2 emissions of the whole construction industry. And even if we look past the CO2 emissions, cement itself is very contaminant. So it is definitely a concern. And sadly, in most third world countries, the price of cement is even higher than in first world countries. So there's also like a socio-economical thing to think about there. And something that I don't hear being mentioned enough is the fact that reinforced concrete is actually not a very resilient material. It usually lasts between 80 and 100 years before the reinforcement rebar starts to rust. When it rusts, it expands. When it expands, it breaks out the concrete. So these are not resilient structures. And in the context of harsh environments like seafront when they are exposed to salt and a high level of humidity, this lifespan is even shorter. This beautiful project that I showed you before, the Unité Habitationnelle de Marseille, has already needed like 3 renovation campaigns because the concrete deteriorates. Even though it's not that old of a building, I think it's roughly 80 years old. So that's one of the reasons why we're starting to look towards biomaterials. And when we try to define it, if you do like a quick search of the definition of a biomaterial, you're usually gonna find initially more information from the medicine side of things, because there has been a lot of interest from the medical industry to produce biomaterials basically to treat us humans. It all starts by thinking of us, I guess. And the definition usually implies the use of inert substances that can be implanted into this biological environment without harming it. You can also start to see some definitions from the side of construction and architecture, and they usually highlight the sustainability of these renewable materials that can be extracted and used without harming a particular environment. So kind of the common thing here is that we're thinking of elements that their production is not particularly harmful in terms of CO2 consumption, contamination of the process, and also that can be implanted into a particular environment without harming it, or harming it the least amount possible. And that's basically how we see nature produce their structures. Trees are highly adapted, very large structures with a very complex microscopical structure. This is a microscopic view of a sample of wood. You can see the fibrous and lignin structure. Bamboo is so to say a close relative, but it also differs in its structure. It has a much denser porosity at a microscopic level that gives it very different properties. You can see amazing adaptations in some organisms, like this is the stem of a plant species that is local to a very hot environment. It receives a lot of sunlight, and plants like sunlight, but to an extent. With too much heat, they're subjected to evaporation that makes them lose water. So many plants in sunny climates develop these hairy structures that gives them some self-shading. So they shade themselves from a portion of the sunlight to reduce the evaporation that might happen. Moss is also a very adapted, amazing, changing structure that can react in the presence of moisture to open up and absorb this environmental moisture. To the right of the picture, you can see these yellow spots, which are lichen, this insanely complex symbiotic organism between an algae and a fungi that allows an algae to subsist outside of water. So yeah, these are highly adapted, highly complex structures that we can definitely look to and learn from. And I'm not trying to say that we should only take materials from nature and use them without transforming them. I think it is also important to reinterpret them in the context of contemporary computational design tools and new technologies in fabrication. Like, for example, there are companies looking towards mycelium to produce mycelium bricks and building insulation. There's already interest in the fashion industry to use bacterial cellulose. There are companies like this studio, BC Architects, who are working on the standardization of soil bricks to ease the licensing process of some of these earthen buildings. the AA has done a very interesting project on the 3D scanning of non-regular timber sections that can allow for the construction of large structures, load-bearing structures that before couldn't be done with this kind of sections because we relied on a degree of standardization. So this would allow for a lot more structures to be built with what used to be considered useless pieces of wood. And ETH in Zurich is also doing a lot of work on robotic fabrication of earthen structures. This is the clay rotunda. As the name suggests, this is a structure made out of clay, so it's not necessarily raw soil. But I know that they are already producing a bespoke soil mix because they want to basically take this technology into a construction process that can be locally sourced. So yeah, these are all pre-existing biological materials that are being reinterpreted into these new construction practices and technologies. Now I'm gonna leave you with Dana, who's gonna introduce us to a talk to ancient and new technologies. Thanks.
Yeah, I love the question, how new is the biodesign industry? So as the urgency of our climate crisis becomes undeniable, architecture faces critical moment of reinvention or perhaps remembrance of ancient technologies. And also we'll go through a little bit of new technologies and what is happening in biotechnology of today, and what kind of tools it can give for architects of tomorrow. So when I put word architecture on Pinterest, these are the main pictures that I see on the first page. And as you can see, mainly this is European buildings and some of Midjourney based images. And as you know, architectural history traditionally taught by the Western world and then all around the world is narrowly focused on the European and some of the other countries, but mainly on European history. And this perspective largely overlooks the first 50 centuries of architectural development and the building practices, presenting only partial architecture that is, a sign of like wealth and politics, and overlooking dwellings of common people on all around the world. And this is a really good book, and there was an exhibition at MoMA called Architecture Without Architects. And so exploring the unfamiliar world of vernacular architecture, anonymous, often spontaneous, indigenous, rural, and called primitive, is often poorly documented, and also reveals how untutored builders have harmoniously integrated their construction with natural surroundings, embracing the challenges of climate and topography. Unlike modern practices that reshape nature, forces nature, these builders valued functionality and environmental harmony, anticipating many modern technological innovations of today. Yeah, so my question is to all these indigenous practices and buildings all around the world, is it really primitive? So I'm going to ask a few questions. I would like it to be interactive. Some of them are just, philosophical. Some of them are practical. So this is a living root bridge by Khasi tribe. This one is located in Northeast India, made out of banyan tree, directed by bamboo, how do you call it, and ladder, and also added by stones and other fibers, plant fibers. And this is a knowledge that passed down by grandmothers, grandfathers to next generation. And it's an incredible technology, actually, where you use a living root structure to build a bridge in this case, and over time it becomes more sustainable, stronger, and the next generation will make it even stronger by weaving the plant fibers further. Oh, okay, great. There's someone from that area, from that community, I guess. Maybe we could discuss this later. We would love to get your opinion on this. And so our question would be, could architecture be redefined as the guardianship of both the natural environment and spaces instead of contributing to ecological degradation? So yeah, as you can see in this image, it's Moray, located in modern Peru. It's Sacred Valley of Incas near Cusco. It's an archaeological site consisting of several terrace levels, where it was an open laboratory, agricultural laboratory, testing out different soils to grow different types of plants and so on. And what if we designed our economies to mirror the principles of Moray, favoring integration, circularity, durability, and a social resilience? And another image is a tree, baobab tree in Africa, where it's hollowed out and used sometimes as a dwelling and sometimes as a water tanks to save water for the next season. Yeah, could architecture be resilient and adaptive to flooding? These are floating islands of Al Tahla in southern Iraq, wetlands of Iraq. And it's built from a single living reed species, and mixed with mud and the dry reeds. And as you can see, it floods, and it's very resilient structures for flooding and the climate change. Climate change differences. This is my heritage. I'm from Central Asia. So Central Asians used to live, or still live, with nomadic, with natural cycles. They move in winter and for summer as well, and all these materials are made from locally sourced wool. That is in abundance here. And so can we redesign, live in harmony with natural cycles similar to the way of nomads do? And each part of the yurt, that is the structure, temporary structure that you see, consists of multiple parts, and each part is connected to the mythology and cosmology that people believe here. Just two tables comparing extractive and non-extractive architecture. Extractive architecture, just to simplify, is profit-driven system where we have design, construction, and maintenance. And usually, as a result, we have, afterthought is environmental impact, energy consumption, and very high waste generation. And construction waste is one of the biggest problems in the built environment, as you know. And non-extractive architecture, or I call it indigenous or native architecture, is based on a very intertwined connection between culture and environment, climate, mythology, cosmology, stories, songs, traditions. And it's always energy efficient, waste reductive, and usually it's in harmony with the environment and the environmental cycles. But is nature ideal? This is one of the questions that a lot of biotechnologists ask today. As you can see, this is Ginkgo Bioworks work, innovation. So they took CRISPR technology. It's a gene editing technology where you can cut a gene that you like. In this case, they found a mushroom, bioluminescent mushroom that glows in forest at night. And they cut the gene and inserted to bacteria. I think it was E. coli. It's like a very well-researched organism that is in our gut. And then they put the E. coli to plants. And as you can see now, we have a glowing plant that does not exist in this earth. So I would like to challenge you to think like where this technology could be used, would be used. Perhaps it could be replaced. It could replace in some places the street lights or interior lights, garden lights, just to make the life of biodiversity, insects, and the ecosystems slightly better compared to our light pollution. Yes, okay, let's go back to this. Another question that I find very interesting to ask you is, can we fuse crafts, cultural heritage with biotechnology? This is a brilliant project by Shnil Malik. She's one of our PhD doctors at UCL. And this project was developed at our lab, Biodesign, by the curation of Marcus Cruz and Dr. Brenda Parker. Essentially, she used the crafts of the area that she comes from in India. I think it's Mumbai region. And in that region, there's a lot of toxic dyes for textile industry, and the water is very much polluted. So she created the ceramic tiles using craftsmen, collaborating with craftsmen. And in these channels, as you can see, the green part is hydrogel and algae. So it's a type of gel that is engineered and for algae to live, living algae to live. And if you pour water and toxic water, and if you run water multiple times, you will see how algae will absorb the toxins from the water. So this is the tile system she has created for London Design Festival, I believe. Another project by our professors, again, Marcus Cruz and Brenda Parker, is Poi Kylohydric living wall. The question would be for you, plants could potentially plants be engineered to reduce atmospheric carbon dioxide? As you know, like we have more vertical spaces than the horizontal spaces. So like the whole square meter of Earth would be less than all the vertical spaces that we have on this planet. So could we rethink how we use the vertical spaces and potentially reduce atmospheric carbon dioxide using plants, engineering plants, right? So this project is in London, is in one of the primary schools. If you are in the UK, you please visit. It's a very beautiful structure. And they researched what kind of materials we can use, bioreceptive materials. So essentially bioreceptive means that the material is receptive for organisms to grow. So it creates enough porosity for other organisms to colonize the structure. And they also calculated and analyzed what would be the good, better microclimates, good microclimates for moss to grow. And here you can see them, moss are growing. And this is another project that they put is in Edinburgh in Scotland. And you can see in these images that the moss and the other organisms start colonizing. So moss is as one of the primary species, and then you have the other species coming. So that's how the biodiversity essentially starts. Very exciting project, how to use passive green wall systems, because usually green wall systems are very energy intense and they uses a lot of plastic. So this kind of projects actually, encourages people to use passive systems. Yeah, so a few questions for you to think. Could algae, ferns, and other photosynthetic organisms potentially facilitate significant atmospheric CO2 drawdown in the building facades? Can you think of any facades that you can use in the area you're from? Could bacteria be engineered to reduce atmospheric methane, perhaps next to agricultural fields? And how this is going to look like, and how might this technology be integrated into architectural designs? Yeah. And yeah, could we shift from the concept of survival of the fittest to survival of the most symbiotic in our approach to design and architecture? And what's the role of architects in the upcoming future? Yeah, thank you guys. This was very exciting. I hope these questions encourage you to think and challenge the status quo in the architectural world. We have 10 minutes coffee break.
Yeah,
right,
we have a coffee break scheduled, but I think we're okay in time. Like it's not even 5 p.m. yet. So if you guys are okay, I wanted to maybe let the participants make any comments or questions, because I think a lot of ideas have been thrown around in your part, particularly Dana, a few very interesting questions. I would love to hear what you guys think,
Yeah.
or if you guys want to make any comments.
Perhaps you can turn on your computer, the video and audio. Yeah.
Yeah, if somebody wants to unmute themselves and ask questions, if nobody wants to ask the questions on camera, we can start reading the chat. I think there are a couple of questions in the chat. Any volunteers?
What are should I read
Yeah,
Muhammad's question? What are the disadvantages, though? These types of plants being harmful to the environment, them being harmful to humans in larger scales, or etc.
That's an interesting question. I want to make a comment about that, Dana. If you want, you can also help me with this one. I think when we talk about harmful, I guess in terms of an ecosystem and talking about plants, you can talk about invasiveness. Sometimes there have been cases where a new species is introduced to a particular plant environment and it becomes invasive, meaning that it takes a lot of resources, maybe from the soil, that are then not available for other plants. So it becomes like a predator in this new environment. To avoid that, you could try to focus on local plants. Usually when you go to any environment, you can find local species, and these species, since they've been there for a long time, they're adapted to not only benefit from that particular environment, but also they are adapted to subsist in symbiosis in the best case, or at least in a amicable cohabitation with other species. So yeah, usually when you go local, you can't go wrong. I'm saying usually because I don't like to speak in absolutes, but that's generally an okay perspective. And when you mention if they can be harmful to humans, there are definitely some I don't know, fungus that might become harmful to humans, but generally speaking, we subsist with a lot of natural things. Bacteria populates not only the outside, but also the inside of our bodies. Before we used to live in brick and mortar houses, people used to live in soil houses and caves, and they subsisted just fine. Actually, the fact that we have grown apart from that reality is starting to harm us. Apparently, there's a chronic B12 or B2 vitamin deficiency in all humans, and that's because we used to get that from the soil when we ingested some degree of soil in our daily meals. And since we don't do that anymore because our food has become extremely hygienic, then we all suffer from a slight, I think it's vitamin B12 or B2, one of those. I'll Google it after. But yeah, we are also adapted to subsist next to nature. So as long as it's nothing toxic or particularly concerning, we can be close to these biomaterials without any negative effect on us.
Can I just add to that?
Sure, for sure.
Yeah, there's also 4 biosafety levels: BSL-1, BSL-2, BSL-3, BSL-4. This are different levels of how you can check how safe your organisms are. Also, you can check papers, scientific papers, how this organism affects, certain ecosystems. If you are bringing something from the UK to Australia, of course, this is needs to be evaluated because Australia has a different ecosystem compared to the UK. So also, although your organism can be BSL-1, so this safest one, there's also a danger of monoculture. This is something I'm afraid of with mycelium, companies that are happening right now. Of course, it's much better than any plastic or foam-based, materials, but still, we are cultivating basically only 2 species, and this can replace the plastic packaging, foam packaging, and so on. But I'm not too sure if there's a research how the whole world will react to 1 species of mycelium. Although it's dried and dead, still there's the genetic information there. So there's that. Monoculture, it can be dangerous, but you have to check that. You have to do your research. But overall, if you're compared to concrete, plastic, and steel, and the whole the material extraction practices that we have, of course, biodesign, even the basic practices, is way more sustainable, and you can compare it. Yeah.
Amazing. Thanks, Dana. Also, I think Walter has shared this degrees of risk, of biological risk. It's super interesting. It's in the chat if you guys want to see it. I'm going to quickly answer some of the questions that I'm starting to see here about Autodesk CFD. If you have downloaded it, amazing. We're going to use that tomorrow. I don't think we're going to need Fusion 360. We're not going to need that, right, Dana?
No,
Okay.
no, I don't think so.
Yeah, we're already using quite a few programs, so we don't want to add new programs to the list. About the ETH Clay Research Pavilion project. That's a question related to day 3, the fabrication day. The idea is that since you guys are going to come up with different projects, the idea is that on the last day, we're going to try to see a couple of different systems, and we're going to try to see which one applies better for the project that you guys are doing. But I am going to show you a Grasshopper script for a toolpath that is very similar to the Clay Rotunda project, which relates to a project that I did on my master's as well, and that I'm going to present on the last day of the workshop. So short answer, yes, we're going to see a script that's very similar to the ETH project. Okay, I'm going to read this to full. In terms of scales and functionality, example, facades and panels versus structures, have any projects explored bio-inspired structural systems that can be utilized as structures in common buildings, since many problems are related to structural systems that are common in building industry? Ed, do you want to help us with that one?
Yeah, so in biodesign and the concept of structures, because typically structures that we use today are chemical bonds or use high intense heat. So yeah, so I think at this point where the biomaterials are not reaching a structural strength level. I think the reason why Ken passed it on to me was because part of my research in my first year was can we make a structural material using biomaterials? And my process, we were using calcium carbonate precipitation. But ultimately, the closest we were able to get was mud brick strength, which can still make small single-story structures. But when we come to the strengths of steel and high-strength members, I think there needs to be a bit more advancement in the process. There has been some precedent, and there's been some research and compression testing of different mixes, but those materials ultimately also have the issue of being biodegradable, and structures typically don't want to degrade. So we're in a phase now where if you would want to make a biomaterial that is structural, it'd have to have a catalyst for it to start degrading. And it's just a kind of a new way of thinking about the way we develop our environment, because you'd have to start producing materials that we then allow or don't allow to degrade. It changes the way we think.
I'm
Yeah.
gonna try to add to that answer and tie it to a different question that I see in the chat. Nandita is asking, to what degree we need to accommodate the biomaterial with the new age material? I love that you called it new age. We're like the hippies of this thing. How to create symbiotic relationship between them, since going full on nature is quite difficult. You're absolutely right. Even if we all agreed that the construction industry, the way that it's being produced currently, is not good for the environment, and we need biomaterials, if we all say, you know what, you're right, that's the right idea, the change is not going to happen like that. There's in many industries there's a lot of inertia. I mean, the way that the industry has been carried on since, I don't know, quite a few times to the way that it's being driven now, and that inertia is hard to fight against. There's a lot of infrastructure that's already adapted to these materials. There's a lot of knowledge, regulations. Basically no industry is ready for a change that immediate. So it's definitely going to be progressive. What we're trying to convey here, or the idea that we're trying to transmit, is that it's going to take some time, but we have to start somewhere. We have to start asking these questions. We have to start seeing how we can start introducing these materials into the industry. Probably the short-term solution is that we're gonna start adding biomaterials as maybe building facades, just cladding, or as something to complement the materials that we already have. And maybe in the future, we can start phasing out those old school materials and start producing maybe a structurally sound biomaterial that can do what the materials that we have today can. So it's gonna, short answer, it's gonna be progressive. It's gonna be a slow process, but somebody has to push it. Somebody has to, be the canary in the coal mine and say, hey, we're suffocating here. We need to shift.
And that being said, I would say like wood and bamboo are definitely biomaterials, and they have been used, and especially like bamboo is very developed in Indonesia, for instance. Now it's coming back in Europe. There's skyscrapers with wood and a lot of innovation in wood materials. iTech at Stuttgart University, they're doing incredible innovations in and development of wood structures. They are looking at microscopic images as well, how to increase the natural properties of wood, how to use it, and also using robotic fabrication and carbon fibers. So yeah, it is coming back. With the new breath. Bala, do you have a question?
Hi, actually, adding a question to the previous question. So the question was how to create this symbiotic relationship between them. So I have a sub question from this. So recently we kind of explore a lot of natural systems getting inspired, and then we build a lot of structures, facade systems, as well as many more structural systems. So, what is your go on all these natural systems that are being inspired from nature, but yet still they use all this new age materials, as you know. So, what is your go? Yeah.
I'm sorry, I couldn't get the last part of your question. Could you repeat that, please?
So I was telling we have all this biodesigns and biomaterials which are being incorporated right now. The question was, we have natural systems that are being used in all building facades right now. Like we have been started to use it, and very recently I came to know about this biomaterials that have been used in a facade from iTech. You know iTech, right? University of Sarkar. So they have explored a few biomaterials on performative and interactive, not interactive very much. It's performance based facade system. So, but there are a few facade systems that are being uh, used and built, which are inspired from nature and natural systems, and but still they have used the new age materials like concrete or any other the mild steel, or that could not be that is not renewable. I mean, that is not a biomaterial. So what is your go on those system of producing structures or facades?
Okay. I think that relates to something that I'm already mentioned. I hope that I'm correctly getting your question. But the idea is that we're not going to be able to produce a building that's 100%, so to say, biomaterials. We're not there yet. The technology is not there yet. So in the short term, we're probably still going to use the materials of the construction industry as we know it, steel, concrete. We're going to try to use them in the most sustainable way possible. And where we can, we're going to try to introduce these new biomaterials. And maybe as the industry and the technology advances and we understand better how to produce and how to work with these biomaterials, maybe in the future, we will be able to produce a 100% biodesign building. I think it was Nettie Oxman who said, I'm not sure if you guys know Nettie Oxman. She was mentioned by Dana in one of the resources that she showed. She's an architect, American, Israeli American, I think. And she has done a lot of work in biodesign. And she mentioned that one of the ideas that drives her design thinking and her practice is to one day get humans to produce structures that are unidentifiable from the structures that nature produces. Because today, if I make something, I don't know, if I build a building, if I build a chair, and I show you a tree, and I ask you, hey, which one of these objects was made by a human and which one of these objects was made by nature? You're very easily gonna be like, oh, the chair, I can see it. So her question was, will we be able to one day make these elements undistinguishable? That when I ask you that question, was this made by a human or by nature, you won't be able to tell. That's an interesting idea. And I guess that's her final goal. Maybe it can be something that we will be able to see in our lifetime, maybe not. We'll see. But that's where we're trying to go, I guess.
Should I read this question? Yeah. Given that plants and bacteria are vulnerable to weather and costly to maintain, do you think it's possible to discover the mechanisms behind the carbon capture and growth, develop more durable bio-inspired machine structures and materials to capture the carbon and achieve other biological functions with much lower costs? Yeah, thank you for the question. It's a great question. I think when choosing plants, especially for green walls, native plants are overlooked. Native plants are very resilient to the environment it's surrounded by. So if you're choosing plant to collaborate or employ, I would suggest you we can definitely choose native plants and bacteria. They are not vulnerable, I would say. They are vulnerable to climate, but not every single species is vulnerable. There are lots of resilient species in biology. But looking at current biotechnological trends like CRISPR, gene editing, and other like biofabrication, bioreactors, we can definitely cut the gene that is strong in this plant and insert it to bacteria to capture carbon more, or create certain proteins that would increase the carbon capturing process or speed. There's definitely research going on at MIT on this topic. But yeah, I would still encourage everyone to use low-tech solutions first, and maybe perhaps later on use synthetic biology or material science, because all these are quite costly and you need a lab and access to university. So yeah, there are lots of low-tech solutions that we showed today, especially at my section of presentation, that are low-tech. You just provide a bioreceptive space and they just start colonizing it. You direct the growth, and plants like vascular plants like moss, they're very, very resilient. They can live in drought and the very humid area under the rain, and in very, very like dry areas as well. So it has like two sort of like modes of living. Yeah.
We have a few more questions. Oh, sorry, go ahead, go ahead.
Sorry, just the last question, and I think we have one more. How can we make biomaterials and biodesign accessible? I mean, this is why we're giving this workshop, just to share the knowledge that we have, and we're also growing and learning. We just graduated from the university, and we're actively trying to work in our regions, like Canada's in Latin America. I'm in Kazakhstan in Central Asia. Ed is in London. We are trying to democratize the knowledge, give back to the communities. I recently gave biopolymers workshop for teenagers, and we discussed, regenerative architecture, how to heal, and cultural heritage. And so I think, yeah, we're all trying our best, and it will be great if we build a community. And perhaps with this, everyone who's here, we can make a chat or, community and share all the resources that we have.
Yeah, I like what Dana's saying, because also it's emphasizing the fact that we are in the beginning phase of this process. So technically, whatever you find, like you can look up biomaterials or a certain material that you want, and often these materials can be made in your kitchen or in your backyard because they're so preliminary right now, and it's not so necessary to have the lab if you feel like you can manage. Like for example, I mean, there's a researcher, Bastian Baer, who's done mineralized weaving structures, and most of the time when you see his process, it's in his backyard. He's doing the work of this amazing like mineralization process in like a non-sterile environment, and it's interesting to see how like we're in this phase where we should be able to do these materials in non-sterile environments, because that's how you commercialize it and expand it. So it can be accessible based on how willing you are also able to just produce it yourself under the process that you found online.
Yeah, I totally agree. As I think, as Dana also mentioned, there's a part of this that, yeah, might be tied to the access to a lab and stuff like that. But there's also a lot that you can do around biodesign, so to say, by just looking at ancient technologies. You can look at how people used to build with soil before. There's a soil construction tradition in a lot of places. South America, in England, they also have a lot of soil construction systems, the Middle East, in Asia. Those are all vernacular technologies that can inform current projects, basically because we have largely ignored these traditions. And if you take some of the information that we have nowadays around, for example, biopolymers, synthetic biology, you can add some of that and just come up with something new. I think the main thing is that you have to embrace complexity. We're talking about non-standardized materials that are, in some cases, not studied enough. So you have to embrace complexity into your process. You have to assume that you're going to go through trial and error. It might not work the first 5 times, but then something you reach a point where it starts working, and then you build on top of that. I think we're going to talk a little bit more about that process in the Edward is going to present one of his projects, and Dana and I were also going to present some more projects in the next couple of days. So yeah, we're going to dive a little bit deeper on that.
Should we take the break?
Yeah, we're going to take a 10-minute break, and Edward is going to present the next section, and if you guys want, we can have a few more questions at the end. So yeah, we're gonna be back in 10 minutes. Let's say 5:25. Is that okay with everybody? Perfect. Okay, we'll be back then. Okay. Guess we can start coming back. Shall we wait for Dana, Ed?
Yeah, we can wait a minute.
Yeah, she should be back pretty soon. I think we can start, and then I can just join in while you present.
Yeah, I think that's cool. All right. Welcome back. I hope you had a good coffee. I'm gonna get into so we've talked about biointegrated design projects that exist, but what we want to explain is how to be a biointegrated designer. So these terms, biophilia and biomimicry, are kind of grandfather terms to that idea. Starting with biophilia, the original concept was that we have this predisposition for nature, and we want to re-include it into our environment. And buildings we spent a long time separating, and now let's start reintroducing. But it was done in a very industrial context. So as we, well, the original terms are coming from Eric Fromm, who's a psychoanalyst. So it was a psychological approach. And the idea is that we need nature in this context around us, but it's more of a controlling instead of a adapting and integrating. So Stephen Kelhart kind of progressed it further in the architectural context, and these parameters that you see listed here were ways that we can include nature into our environment, our building environment. But it was all under the context of we need planters, we need fish tanks, you know, not necessarily that we are providing for organisms as well. The next term, biomimicry, is again more industrialized and kind of more stereotypical way of understanding nature. We just take forms and we turn them into these man-made structural elements that look like the imitation of what was pre-existing. And what's I find problematic with this one is that it doesn't focus on the systems as much as it is the actual design. But with the combination of the two, you start getting closer. I think Benyus was quite close as well, because in the concept of biomimicry, she was talking about taking inspiration from the processes as well. So it was on its way to start thinking as a biodesigner, but I think it was all under a very strict architectural context. Like, for example, when Brunelleschi worked on the Florence Cathedral, the dome was shaped under the research of the eggshell. And this is something that helped with structure, but it didn't quite translate other than a literal and formal way. As you combine the two into biointegrated design, you start thinking about how to work for organisms and the people and the environment. The idea is the collaboration. So when you find a site, it's very common to find sites that are problematic, like brownfield sites or things that have they have issues with some sort of lacking organism or too much human interference. And the idea is how you develop past those to provide for both people and organisms. This is a diagram kind of showing how in the standard design process, when you're doing typical architecture, the pre-design and site analysis is a basic environmental under the context of openings like windows, lights, and airflow. But once you get past that main point, for the rest of the process, through schematic design all the way to construction, administration, you see that the drawings are the main element that are the focus. The materials are never a discussion. They're expected, they're understood, and they don't consider living organisms on the site. Biodesign, on the other hand, is heavily rooted in research and is constantly reaches back to biological organisms. So as you do the site analysis, you're not only researching what is in the environment, but you're also researching what was pre-existing there, what's living there, what's lacking there. One step that gets added in this process is identifying a problem, because it's almost more often than not that you find these contaminated sites or problematic locations because of some sort of interference or an imbalance in this organism, in the system, in the ecosystem. And so through that, then the design starts being created because of the issue. And this typically results in a realistic and fabricatable context. So you start developing this thought of, well, we're trying to solve a problem for organisms and people. So you develop a new method of developing spaces. And at the same time, you start having to reconsider the way that we start considering the way that we have to do materials too, because typical standard materials in that environment would be only increasing the problem. And so naturally in the biodesign process, you find out that you have to constantly be researching from site to learning about the problem to designing for these organisms and systems, and then ending up having to create materials that work and provide for them. And I'm going to go into a case study. It's my thesis project. I worked also with Natalie Risk and Rita Muha. It's just good to guys show you how this process went because it helps give a clear idea of the way that we have learned how to think in a biodesign context in an architectural setting. So beginning is the site location, picking a place. We picked Pegwell Bay. It's in Ramsgate. It's this hovercraft port site that was abandoned. So it's this big concrete pad that's barren and just now is left to have just residual growth occurring, but is actually quite a dynamic environment in its surrounding context. So if you go just I don't know, maybe 10 meters south or north, you can find these chalk cliffs with these tide pools, and you start learning that the original environment was much more complex and fascinating space. And so we found it interesting, and we decided the first step to any biodesign project is to do research on the location. This is just showing us going through the process of analyzing, studying, learning about the space, and finding out what we can work with. Through that, then you start developing diagrams that show what is possible to grow there, what is growing there. It's important to find a diverse and like even level of understanding of all the organisms, because it's very easy to focus on one and then over design for one, which causes a problem again. So the idea is that when you research everything from mineral compositions, even keystone bird species, seaweed cycles, things that start expressing different also design languages, you start formulating and considering what you can do for the space that is now barren but could be providing much more for both people and organisms. We ended up finding the problem was, which was somewhat given, was that the tide pooling was necessary. That site was originally a tide pool location that got buried up. They used colliery waste and concrete to cover it, so you can't even dig into the concrete no more because you'll start releasing all these toxins into the ocean. So we had to consider how to work with this concrete pad and still provide these tide pool parameters. The concept then came from the two parts, mangroves and seaweed holdfast. The seaweed holdfast was the concept on holding onto the surface of the concrete pad, different ways of kind of being able to carry a structure without a literal foundation going into the earth, while the mangroves were a solution on how to help with the new tide pools that we were going to provide on the site. Because with the waves, and we needed a wave breaking system that would be also part of the structure in order to help this new growth that was going to occur. So we designed these tide pool tiles that, based on our research, had the varying parameters and depths necessary for a wide variety of species. We also did analysis. This is CFD, which we'll get into later on day 2, to understand the amount of branching was necessary, how much flow defense we needed, and also if there was necessary additional elements like groins to help with the reduction of water forces. And then after many iterations, this is the final one, but to get to the final iteration was this process of constantly researching both organisms, solutions, and designs, and resulting in a structure that could be used by people along with being used for growth and new environment, and kind of revitalizing a space that needed a bit of love necessarily. So with this concept of the branching, what happens is that you have to start considering how to make this structure. It's a complex system, and we're trying to be realistic. We're trying to create for people, and so what happens is you start researching deeper into the fabrication method as well. And so in this particular one, with this shortest path structure, the original elements were then researched and made into a kit of parts, and they were all uniform. And using aggregation, we were able to start forming connection members. And then once that was considered, it was the actual fabrication process. For me particular, it was using PLA to 3D print molds that then became casts that you can start connecting members across piece to piece. So you see how the iteration goes and develops in more complexity as you work through the issues and conflicts that come with developing a new design process and using new biomaterials. And now that you guys have kind of seen kind of a crash course of a project, we're interested in having you guys kind of go through that process. So we are offering kind of to use the same context as the project that I had worked on. So a tide pool, a coastal like site, we want you to consider a location that you may already know. Maybe spend 10, 15 minutes on finding something within groups of 5. We have a mural board that we're gonna share with you guys, and you'll be able to fill out your names and start working in teams. We have rooms in Zoom, so we're gonna let people break out into their rooms and work, and we'll always be here for questions, because what we want to emphasize is that the process is the important part. So don't necessarily dwell on the design as much. Handle the thinking, and we can help support you for that. Once you find the site, if you don't want to find the site, you can use the Pegwell Bay Ramsgate location that I had used. But once you find that site, the analysis, which is more complex than just wind and water flow, but maybe thinking about what organisms are common there, if there's any issues, is there something missing, how often is it used, is it a public space, is it a private space? And then we get into some preliminary design. So go get a first pass at how you think you would work to handle helping the organisms, like handle providing space for people at the same time. Feel free, don't worry about material. Think about how to just develop context for both people and the environment. So, yeah.
Ed, can we share those links in the chat? Because some people might not be able to copy them from the presentation.
Cool. I can stop sharing too.
Nice. Anybody want to jump in for a question for Ed, maybe in the chat or on camera?
I have a question for Ed. Ed, I love the presentation. I'm currently doing coastal stewardship in New Jersey, USA, and we have a very similar but exactly different problem than what you were solving with the mangrove and the hold-ons. Basically in our bay, the sedge, the grasses, get surrounded by the different shellfish and protect the edges. And with all of the boat traffic and I guess climate change, they've documented, New Jersey took pictures in 1978, and they've been able to document the soil erosion. So in a class 3 weeks ago, they were talking about how they're trying to fix this, and they're putting in concrete things and these oyster castles, and they were all kind of cute. But it didn't seem like any of them got to the problem. And it seems very similar to what you're doing. And I guess, so that's a little bit of my explanation, but where I thought the answer was going in terms of what you were doing is kind of in more of a in situ 3D printing solution that could be done to both anchor into the ground, create that kind of root type structure that the shells could attach themselves to based on certain concretes and I'm not sure if I have a question as much as like I think that would be really fun to work on for this because what you're doing is really close to where I thought we needed to go, and I can pull up the presentations and have really good access to all of the local coastal stewards that are doing this at 4 different colleges, and would be a nice product to have from, you know, what we're allowed to do here for a couple days.
Mhm. I think
Like I was going to do it. I was going to do it anyway, so it would be super fun.
I
And
think the like branching structure is like when it comes from a parametric process like Houdini, it becomes a little bit too complex because you have to create too many member types. But the concept itself of mangroves is an important thing to consider because it's already a natural and great way to handle wave breaking. I mean, we have also the groins that use typically, but they're not handling kind of that small scale reduction. So I think if you wanted to handle the in situ 3D printing, I think it's just about simplified branching process. So how can you have a more, I don't know if it's in like you, instead of printing on site, you print members and then figure out connections and then you build it on site. Or if you're going to 3D print, you would need to consider like, how obviously there's gravity forces and water and things that are going to stop it from being able to dry in a certain time. So
right,
uh, the there's a lot of environmental conditions that affect in situ 3D printing for biomaterials, or I mean concrete also. That's just in that context, the waves in general are going to be um, quite disruptive. So that I personally started leaning on the kit of parts method because I tried originally to deal with 3D printing, and although I was able to print some members, real quick, Ken, can you give access to the mural board?
For sure.
Uh, um, I was able to print some small scale complex structures, but it was failing at certain points, and that was in a very controlled environment already. But it's a quite a big problem globally because I didn't think I left Florida to come to London, and in Florida that was an issue already. And I was like, oh, I won't see it here, and then ended up working on it here anyway in the coast of London. So it seems like it's going to keep happening, and we're
so
not,
is that on the
yeah.
Atlantic coast in Florida or on the Gulf?
It's not necessarily no. Let's check. I'm. It's both. I mean, it's the Gulf is on the west side,
Yeah,
and then Caribbean south, and I was on the Atlantic, but I was in Fort Lauderdale, so and I was along the east coast of it, so that side is more commercialized, and so they bring in the sand and they constantly repopulate and try to they spend tons of money trying to reintroduce sand from other countries into the beaches in order to keep it from uh you know getting washed out. But the West Coast is something not really spoken of quite that much, and it's a little bit less intense on that side.
cool. Thank you.
Yeah,
Looking
thanks
forward
for the
to
question.
learning more. Like I'll try to put something together for tomorrow.
Yeah, that'll be fun.
Amazing. I
Yeah.
hope this is, yeah.
Copy and paste.
Hey, how are we feeling, guys? Ready?
Never ready.
Fair enough. Fair enough.
But happy to show you how not ready we are and see what you think.
That's usually more interesting.
Yeah.
Cool.
Okay. So is it okay if I share my screen?
For sure.
Sure,
Yeah.
we can see the
Yeah.
mural board as well already. So if
Yeah, you know, the tough part about that is zooming in, right?
Yeah, Dana, I think you're the host right now, so maybe. Oh yeah, he's already sharing. Never mind. Yeah, we're good.
Okay. So um so like I need a more zoomed out diagram, but on the coastal United States, coastal everywhere has barrier islands. And the barrier islands kind of moved around and ebbed and flowed and were mainly composed of this type of grass that's called sedge. And at the edge of all of the sedge was always these little guys called rim mussels. This isn't, it's a Shutterstock picture, but rim mussels. And together they worked against kind of the wave action to protect themselves and to kind of keep themselves expanding over time and protecting like the mainland. Like without barrier islands, the mainlands are a disaster to the ocean. So over time, they've started documenting the size of these, and they've noticed since they first started doing this, so this is kind of recent history, since 1978, that these edges probably came out to about where you see, kind of the lighter parts, like everywhere that's light in this diagram is where the ground is closer to the surface. So all of these islands were larger, all of this, and some of it's extreme. Like some of this used to come out, like double this size and really help protect it. And
Wow.
in the last 10 years, it's become an area of concern, especially since like the superstorms and Sandy, that they've recognized that around the world, all of these barriers are kind of going away because of maybe global warming and sea rise, but everybody thinks it's more of this kind of idea of coastal erosion. And kind of this is the way that wave action would work, and the waves would hit up above and they would sculpt underneath and the land would come over and fall over. Well, because there's more boats than there's ever been, this really happens a lot. So um, on the whole East Coast, people are starting to come up with all of these very creative ideas that kind of work and kind of don't work for ways to bring back this barrier edge. And it's starting to be a really big new area of study in the universities that have coastal programs. So like this one's kind of this kooky idea of tubes, and it's pegged in and it lasts for 2 years and then the tubes float away, doesn't work so well. They've started having ones that are a little heavier, that are harder to float away. So they call these oyster castles, and oyster castles are, like I like to call them cement blocks, that they put out there in these really unimaginative patterns, but they do pretty well at becoming the home for algae and mosses and oysters and mussels and become an edge. They also started deciding that they would collect the leftover shells from all of the restaurants and fisheries and put them in bags and put these bags out there. And over time, like the bag becomes not a bag, and it becomes part of the plastic problem. And then the shells fall apart and they lack structure. So, and then this is some of the, kind of the farming for mussels and oysters and clams has diminished in the last century to being about 1% of what it was in the 1900s. So they've started populating the shorelines with kind of shellfish hatcheries. But it would be better. So the islands are shrinking. The shellfish are being overfished. They're trying to come up with ideas where they put a barrier out and then like the sand comes back. They're trying to dredge the bay because there's more silt in the bay than ever, but they can't dredge it because there's no property owners that'll let people put the dredging on their properties. So I think, like, I love this idea, Edward. This is your fault, but this is something that we were looking at. The most effective coastal management tool that exists out there today are the mangroves. Mangroves have these little areas that kind of let the water and fish go and keep grabbing the sediment and allow the vegetation, like there's kind of a higher upland vegetation as well as a lowland vegetation. And then there's the super cool, buy it and attach it onto something, where you just put in something. So this is probably a pretty good answer for people that just have their docks and the sea nettles have grown and have populated more. So this would be great to introduce to them for that problem. But this is kind of a more engineered solution than a biophilic solution. So I think what anybody from the team that wants to take over, we've started identifying lots of issues. What kind of biodiversity, what's wave action, what's the, like, what are, the bay rises a foot and goes back down, what are the parameters? What are our parameters? And somebody made this list, and we're trying to look at a whole host of different ideas. So we're trying to figure out how to completely identify all of the answers that haven't been so successful so far. So there's about 6 of those, but they're almost successful. They're almost successful. And I think that maybe logically, in the world that thinks that 3D printing is going to solve all of our housing solutions, maybe there's a way that there's a coastal version of 3D printing that can keep these edges and sustainability of this edges in a way that, in that quote that I went and looked up from Neri Oxman, that maybe you wouldn't be able to tell the difference with a little parametric modeling and 3D printing, and if not, we can list the questions that aren't so answered yet that we need a little bit better answers for. But I think that's, guys, did I summarize that okay?
Yeah, perfect. I think that's where we're at right now.
Yes.
That's good. You have a site, you identified a problem, you have precedent, you're on the right track.
And
Yeah, I'm actually this sounds super interesting. And tomorrow, Ed is gonna help us teach a section on fluid dynamic simulations on
Exactly.
Autodesk CSD. I'm actually super curious to see how these mangrove structures can potentially help break down the strength of these currents. Maybe they're more efficient than just putting like a bulk massive object.
Kenneth, you nailed one of the biggest problems. You absolutely nailed it. Like the fluid dynamics is something, maybe the rest of our team knows a lot about, but
yeah, well, the software is fairly straightforward to use. It only requires being mindful on how to synthesize your geometry because it is quite computationally heavy. So just stop me if I'm making the wrong assumption. I'm assuming that you guys might want to explore that kind of project. If I were in your team, simulating the whole mangrove structure, the program's gonna crash. So I would take like a horizontal section, like if I sliced the cake of the whole structure on the middle and I just took that middle section, I would put that in a box and I would simulate the water flow from the front on just a section of these interlocking mangrove finger things. That way you could potentially get a simulation that's efficient enough to run, and that gives you enough information on how these structures break out those forces. Just an observation for the future, for tomorrow.
That's assuming if you end up doing mangrove structures, see if that's the direction you go. But
yeah, that's
well, maybe it's not. Biomimicry doesn't mean we have to copy what the mangrove does.
That's a great way to see it.
Maybe there's a version that's somewhere between a mangrove and a ribbed mussel, so that they're
Working intertwined.
It's a so that it would seem as much like the nature, like none of this stuff that they've done so far. I was surprised being in these lectures and everybody, patting themselves on the back and,
Floating away.
this thing, then there's this thing. And I'm like, I guess if that protects your island, that's better than not.
Yeah. I recommend staying in that mindset and that context of how do we start combining elements, because that's how you start creating novel solutions that actually are effective and like blend into the environment better. Like I mean, after doing my project, I recognize there's a little bit of too much biomimicry, and I think it's a good approach to say, how do we start combining new ideas in the same situation?
Do you guys know this project in the Great Salt Lake by Robert Smithson?
Yeah.
Kind of one of the land artists. So, like I think this is one of the more beautiful pieces of sculpture that was ever made on Earth. But like, I think that there could be a version of this that's supernatural that works with wave action, and is a little bit different. And maybe it's what all of this stuff used to look like. Maybe
you can take approaches like growth patterns of oysters, for example, and just studying how the way that they grow be the way that you aggregate elements and things. So thinking in that context would help.
Guys, Dana just mentioned something important. We are running out of time.
Yeah, sorry.
I think you guys are definitely on the right track. So yeah, amazing ideas.
And tomorrow we're going to do the fluid dynamics, right?
Yeah,
you'll get a basic understanding of that.
We're gonna start with 3D modeling with a tool that allows for interesting kind of topographical modeling. And then Edward is going to introduce also the fluid dynamic simulations. And yeah, So is there any other team that we don't have to go through every team if not everybody wants to present, but if anybody has anything else to show us, this is the time, this is the moment.
Hi. I wanted to for our team, team 5.
Yeah, sure. Do you want to share your screen?
Oh, yeah, I can do that.
Or we
sorry.
can go to the Miro board if you want
I
to.
have to leave.
Yeah. Yeah, if you could just go to the Miro board. It's not too much information, just so we
Okay.
get an idea, so how to
Fair
approach
enough.
tomorrow.
Yeah.
Okay. I don't know if you guys can see it. So actually I might just share it. Give me a minute.
What room are you?
I'm gonna share it on the main room. I
Okay.
can do that. Share. Sorry. Share screen. Wow, design. Okay. Okay, so we have had to well, we're focusing on Blackpool Beach, and it's in the UK. It used to be a very big fishing a big beach spot like early 1800s and even in the 1900s and previously. However, with people can be able to go overseas, and the fact that now it's not considered people aren't considered safe. It's not considered safe to bathe in the waters, and it's due to pollution. So specifically, a lot of runoff issues. So storm and emergency runoff, the sewer systems when overflowing when there's huge amounts of rainfall. And as it's an urban area, it has very little agricultural land to soak up the excess rainfall. We want to go further into looking into native plants that could purify the water, as we couldn't block them. It would be unreasonable to suggest maybe blocking off such runways. So we as a group have been looking into maybe native plants, and this is from the Planning Council of Lancashire. And yeah, just looking, for example, the alder, the Alnus glutinosa, it is able to purify water in waterlogged soils. And yeah, so just looking more into native plants that purify water and having a system that would do so. That would be in our structure. So that's kind of the idea that we're going
Cool.
with. Yeah,
That
we need
sounds
to further
interesting.
research.
Yeah. I guess in this case, I would probably suggest that you guys check how these plants purify water, because
Okay.
for example, if this plant purifies water through its root system, but
Okay.
it doesn't survive in a coastal environment, then it's not going to be close enough to perform the purification. Or but I think that's kind of the right way to think about it. Maybe there are some algae that help that. Also, you can take into consideration that you don't necessarily have to like solve something in an active way. Like if you can provide a structure that also allows for natural species of the area to grow, you're already making it a little bit better. But if you're decided on purifying the water, that's also like a very valid avenue. And I think you wanted to say something. Oh no, I was mentioning network.
Oh,
but
sorry,
if
I apologize.
no worries. If you guys, I think it froze. Yeah, if you guys want to go on, it's fine.
You could also. Hello?
Yeah, we can hear you now. We can hear you
Sorry
now.
about that.
Yeah, no worries.
I was gonna just say that you can conceptually think about how the plant purifies water, and then that could be the design approach. Maybe you study the process on how it does that cleaning, and then utilize elements or building elements that would then follow that process without necessarily utilizing the plant exactly. It's just another way to go about it, and I'm just kind of broadening the horizon on the way of thinking about the research.
Good night.
Thank you. Thank you.
Cool.
Mhm.
Is there any other group that wants to, or sorry, I didn't ask you if you had any other questions, Nadia?
No, that was quite helpful. So I would look into process of how it purifies and would kind
Okay.
of go forward. Yeah.
Okay, cool.
Yeah.
Um,
I don't know how I don't know, anthropomorphic this idea is. So you said the guys gave really good idea of looking at the processes, if it attaches to the soil or does it grow without much, depth. So so maybe you can create a technique to sort of like grow plants and then grow other put seeds and grow other plants, and could be maybe like an agricultural even project just to clean up the coastal area in the UK that you mentioned. Yeah, like how aquacultures work, where people grow algae, microalgae. Yeah, so similarly, could be like a phytoremediation project where you remediate using plants.
Okay. And I actually do have a question. The area actually had a lot of naturally occurring algae. So is there a way, or do you think that we could utilize that?
For sure, for sure. Algae usually cleans the water that it's into to some degree. And for example, you have a pollution problem that has to do with sewage runoff. That
Yeah.
means that there's a lot of contaminants involved, bacteria, maybe potentially even viruses. And you don't need to clean everything. Just as long as you clean one of them, it's more than enough. You're already helping. Maybe check if any of the algae that's naturally occurrent in the area can help in any way.
Yeah.
And that would be good enough. And algae, you can usually, just through texture, you can usually help in the bioreceptivity for algae. So it's quite simple once you know which organism to work with and what parameters to pay attention to.
Just
That's
to
really
piggyback off Ken, sometimes it's good to also look into why there is an abundance of algae in that location. It could already be resolving something because it likes to eat something. So
True,
it might be solving your problem already by chance, and that'll be good for you.
Yeah, but also it could be a problem with algae blooms, right? If there's lots of cyanobacteria, it will cover the first layer of water, and then there will be no oxygen availability. Yeah, I would just question what's the core of the problem and why there are lots of like cyanobacteria or chlorella. There could be a reason. Also, one more idea for you. If you are creating, for instance, let's say aquaculture to remediate the water, for if you would like to create something like plastic, you can use macroalgae to create bioplastics from the area. So you can even fill up the macro, algae with microalgae that could, soak and absorb the toxins from the water. This is just an idea for you.
That's really interesting. Thank you.
Cool. I think we need to move on to see if there's another team that wants to show anything. Any volunteers?
I think in room 2, we are a little bit confused. We have many ideas. Can share it.
Room 2.
Yes.
Okay.
Guys, you're there? From room 2?
Yeah, we can see the Miro board. So yeah, what kind of options are you guys considering, or or do you have more of an idea of the problem that you wanna address? What's
Yes,
the topic here?
I can share my screen.
Yeah, sure.
Sorry.
Mm-hmm.
Guys in room 2, you can help me on in order to proceed. But for in the beginning, we have the idea of river banks and how it can help in the erosion preservation, and how can vegetation help to purify the air and water. And the other idea was in the sorry, in this area, Danube River. There are also some high level of pollution. So we are thinking about the two idea. Yes.
Interesting.
So I don't know, guys, if you want to add something in room 2, guys.
Yes, sure. So for the last moment, we stopped at the idea of riverbank flood mitigation, but it was divided into two aspects: preventing soil erosion to keep the vegetation growing, and actually flood mitigation. So we distinguish it as two different problems, right? And we started from the problem, and I don't think we settled on a specific river or specific place.
That's okay. For example, you mentioned the Danube River. If I understand it correctly, that's quite a big river, right? And it goes through natural environments, as well as, I presume, it must go through a city as well. Can you guys confirm?
And yes, and a few of us actually, as far as I understood, at least 3 people lived close to the Danube River because, yeah.
Cool. So if it's, for example, in an urban environment, you could potentially think of a project that's kind of like between urban infrastructure, like sort of kind of a public place next to a river that somehow helps with either the biodiversity in this waterfront space, or maybe you could think of producing a waterfront structure that has some sort of cleaning agent to clean one of the pollutants of the river, because you mentioned pollution. And you could design this structure to kind of erode slowly away with the current of the river, releasing an agent that could clean the water. Or maybe you can identify like an organism that's local to this river that could also help with bioremediation. I guess it's a kind of a big opportunity because it's a big river and it goes through many different places. So you can choose a particular place and try to design for the place and for the problem that the river presents.
Yes, I think we can go in this way. Guys, anyone want to add something, for example?
I think we also had a bit of a problem to visualize how the CFD simulations could like help us in this process. So, for example, the growth of organisms not connected to like CFD simulations that much.
For sure.
But the flow of the river, flow of the air might be. So just to like kind of, if you could give us some example of like how this CFD could like inform this thing that we are building, or if we should first start with something and then like optimize it with the CFD, because that's also another aspect.
Yeah. Well, the CFD simulations is one group of the simulations we're going to show you guys how to use. We're also going to show you how to use solar radiation simulations that are going to allow you to see how much hours of sunlight or energy, depending on what you prefer to get from information from the script, per year or per time of the year. You're going to be able to program that. So in some projects, I can see the fluid dynamic simulations being more important. In some other projects, I can see the solar radiation simulations being more important. For example, if you wanted to say, I want to produce a structure that's going to allow for algae to grow, then the texture for the algae to cling to is definitely one important thing, but also how much sunlight is hitting that piece, because algae also needs sunlight to grow. In the case of the coastal defense project that the first group that presented was mentioning, maybe in their case, the fluid dynamics are a bit more important because they're trying to reduce the strength of these waves against the coastline. So yeah, in some groups, some simulations are gonna become more important, and in other groups, different set of simulations are gonna be more important. It's gonna depend on what you're trying to do. Ed, do you want to add something to that?
I think the last thing that you said is what he said was important, is that the CFD informs modifications, but going through a first pass by understanding a natural process or emulating something that is currently working in a natural environment, and then doing a formal analysis in order to see if it's actually doing the thing that you want it to do, and then modifying based on that is the way to go about it. CFD is the way we're going to use it. It's typically a wind flow, but you can use it as water flow and directional water flow. So the way we're going to use it is a very basic kind of how it impacts and how it flows across surfaces. So it's going to be in that specific context, if that helps inform you.
Yeah. Oh, sorry, you were about to say something. I just wanted to add that you guys should also start designing, and then the simulations can be run on the designs that you start to create. But yeah, it's an iterative process. So, you don't necessarily have to wait until you get all of the information to start designing. It's always good to get something rolling.
Mm-hmm.
Does anybody in your team have anything to add, or maybe we can see one more team before calling it for the day, maybe?
Can we speak for team three, maybe?
Yeah, for sure.
Thank you.
Go for it.
So let me screen. So we are team three. We approach it a little differently. That we are not dealing with water, but we are trying to deal with the leakage of water. So we kind of look at the drought area in the US, and then we find it's more a condition specific instead of site specific for the drought issues, and we are trying to see how biodesign can kind of mitigate the drought issue in this specific kind of climate. And we also look into kind of different species that they can survive in these dry areas. That we wonder like what kind of infrastructure that can conserve waters in this area to kind of try to moderate the the problem. So I'm just wondering if we are going to the right direction, and wonder like the question that was asked before, that how the simulation can help us develop the design in our specific condition that you mentioned about solar and water turbines. But I feel like this is a little. I'm not sure how simulation would help in this kind of specific topic.
Yeah.
Can I also add something? I'm also from
Yes.
his group, group 3. Yeah, we were also interested in drought, but also for me personally, we did emphasize on that as condition specific and not site specific. In that case, I'd say US ended up being just a random decision, but we have a lot of drought problems, for example, also in Kazakhstan with Aral Sea. And also across Europe, for example, Palermo, Sicily is struggling with droughts also. But what's very interesting for me is how we can re-moisture the soil, because when soil gets extremely dry and flaky, its water storage capacity is decreasing. Like how we can reverse the process, how we can help it. If you look down the maps, Eddie, can you maybe scroll down with drought maps and water soil content, like soil moisture map, and we have precipitation, and we were also thinking about fog and the dew harvesting, and I pulled out a moisture map, humidity map down there. So yeah, working with moisture is not too bad of idea in their region, even though the precipitation is very low. We do have still some moisture in the air. Yeah. So what do you think?
Yeah, this is all super interesting. I think I'm gonna start by trying to answer Eddie's question about how, for example, I would approach trying to get information from the simulations to inform this design. So I think in the case, if I understand correctly, the purpose of the project, in the case of this particular project, I think both simulations are important. First of all, talking about the solar radiation simulations, if I wanted to produce a structure that collects water from the air, then wherever I store this water, I want this place to be as protected as possible from solar radiation to avoid evaporation to the maximum, right? So part of my simulations would be, okay, how can I produce a geometry that not only collects water from this environment, but wherever this water falls, I want to protect that part from solar radiation, right? And if my geometry can do both at the same time, amazing. And that's going to take figuring out some information about where the sun comes from at which time of the year. You probably want to protect the summer months of the year more than the other months, because it's quite hard to protect from radiation all around the year. And in the side of the fluid dynamic simulations, I think you guys showed the picture of a beetle that can collect water from the humidity of the air. And that's, if I'm not mistaken, that's done by the geometry and the texture of the shell of this beetle. So you guys can probably study how this beetle gets to collect moisture from the air. I would assume that he would line up its body to get as much airflow going towards him, so that he can collect.
Yeah, he actually stands up vertically, like with his bottom up, so to say, and with his mouth down. And the texture of the shell is so bumpy, and it has the cavities and these bumps. And actually, material-wise speaking, the shell structure is made of these cavities and bumps that are hydrophobic and hydrophilic.
Cool.
So the hydrophilic ones actually trying to catch some droplets of water from the air, And the hydrophobic ones, they are like network guiding, to slide the water down to the mouth. Yeah, that's how it
Okay,
works.
that's super interesting. Yeah, in that case, you can try different geometries and with the different angles, for example, for this element, and with the CFD fluid dynamic simulations, you can check which ones can slow down the wind more, because the slower the wind gets while it's hitting your surface, the more interaction it's gonna get with your surface. So the simulations of CFD are gonna also allow you to test which one of these iterations is more efficient to catch the wind. So yeah, I would say if that's the path that you want to take your project in, both simulations are quite important.
Okay, thank you.
Thank you.
Thank you, guys. Any other group or?
Oh yeah, I had this question about healing the soil and
Yeah, go
like
for it.
how you remoisture it. And I think we skipped this question. If you could elaborate on that.
Yeah, that's that might be, you could potentially identify it as a different project, or maybe it could be a related project. Maybe the reason why you're trying to collect water and direct it to some space is to avoid having this space dry out too much. Because yeah, I'm familiar with this event where if soil dries up too much and it gets like a bunch of water in like just the span of one day, it doesn't absorb it. It loses some of these absorption properties. It is much more efficient to have like continuous rains, even if it's like lower frequency, lower quantity. It's the frequency that's better for the soil because it allows it to absorb moisture properly. I guess you could potentially say that the structures that you guys could produce to get water from the air are maybe not designed to collect water for human consumption. Maybe they are designed to keep a portion of this land continuously moisturized, continuously wet, so it doesn't dry up and it doesn't lose these absorption properties of the soil. I think both ideas could connect one with the other.
So if we simplify it and put it this way, that we try to catch water with our structure, then collect it for the purpose of remoisturing the soil, then we also need to think about the irrigation process. So it's not just like just one water tank that is just collecting water, but also like how like the strategy of giving it back to Earth, but also keeping in mind that just dumping water on it won't work. It's rather slow process. So
true. I guess I wouldn't imagine it as one big element that collects like one tank of water. Maybe it's like, imagine if I were to have these structures like these beetles, but not that small, maybe the size of a small mound. And I don't have one, I have like 100 of these elements. Then I have like a big piece of land that has its own nodules of moisturization, and it can be addressed as a maybe agricultural project. Like maybe I can keep this land apt for agriculture. This is completely arid, it's barren, it doesn't have any moisture. I'm gonna produce this 100, like almost like a land art installation. I'm gonna produce 100 of these small mounds that replicate the system of a beetle, and I'm gonna regenerate this land. And maybe 5 years in the future, or I don't know, maybe just 2 years, depending on how much moisture it can get from the air, this area is not arid anymore. Maybe it's a little bit regenerated, and I can plant something here. You know, it doesn't have to be one element. It can be hundreds of elements that collectively have a big impact.
Great. So it's just like a long-term mission project.
That's the thing. When we're talking about these biodesign projects, some of them are just going to take time, and we should also be able to embrace that longer time frame we should sometimes try to look past our own lives, you know? Maybe this is a project for 5 generations and it's still worthwhile, you know?
Mhm. And also, I had a question regarding aging simulations. Like, are there
Erosion.
any kind of yes, erosion, but also uh, if you have some organic substances, can you simulate their decay, so to say?
Yes, but that's quite a complex question, because designing these models computationally is usually quite heavy. We're getting better at that, but it's kind of a new area of computational science. Dana can probably tell you something about that because she did a lot of work around erosion in Houdini, and she's going to show you some tools around that tomorrow. But it is well, then I can probably take this question. It is a complex question.
Yeah. So as my professor says, so erosion tools that we use in Houdini are not, you know, calculated. Their anticipation of trends, hydro and thermal erosion, and we can see over time how this textures, you know, will erode over time. So it's also important to know the material that you are using. If it's a new age material, like mycelium, we don't have enough information in computational design to simulate the decay, because mycelium materials can be engineered. You can engineer it as a leather, you can engineer it as a brick, you can engineer it as a acoustic panel. So it depends how you engineer it. Similarly to wood, yeah, wood has like a general natural properties, but you can also, you know, have a laminate, you can have you know, different, like you can glue it differently. So depending on the glue and the resin that you're adding, you can have a different aging properties of the same material. Yeah, earthen materials wise, that was one of my thesis, first year thesis. We simulated using vellum in Houdini, grain structures, how to essentially simulate robotic fabrication in Houdini, because the robotic fabrication simulations in Grasshopper are not designed for soft materials or granular materials. But however, what I found is it's really hard to simulate because of the computational constraints. And decaying is also not easy to anticipate, because you don't have only rain, you don't have only thermal, you know, input, you have multiple inputs, wind, rain, you know, you have human impact. So it's not easy to simulate. We have the general tools. Maybe if anyone else knows in the chat. Maybe mycelium grows in the desert. Perhaps, yeah, because it has hydrophobic properties, right? But Karagozem, I loved your idea, and I think what Kenneth has proposed is really interesting. And the like beetle-like structures where you have partially hydrophobic, hydrophilic to collect the atmospheric droplets, and then also sort of like protect in certain areas from the solar radiation. I think it's very interesting, and having like multiple small solutions around arid areas. It's a really fascinating idea. How did you teach these for your design process? We used Rhino, Blend, Houdini mainly. That was the main program in our program. Yeah, our program encouraged it. Javier Ruiz, one of our tutors, was one of the first architects who used the VFX tool, Houdini, for architecture, like, I don't know, 15 years ago. He actually pushed at Bartlett to use it for students and use it for architectural tools. So all of this like development that you see is, you know, started from Javier.
Yeah. Oh, sorry, Dan, I got you.
Yeah, just saying that I'm gonna teach tomorrow, but I'm not a proficient in Houdini. As a lot of people say, it's very difficult software. So a lot of people know piece by piece, you know, so I know Vellum and the height fields, a little bit of solvers, but I don't know much about like destruction, simulation of other types. We're also going to teach you rain if you need, because, you know, you said like you're going to collect rain droplets, perhaps atmospheric droplets. Perhaps we can also show rain if we have enough time tomorrow.
Yeah, as I said at the beginning, we're going to show all of these tools, but this is not a Houdini workshop. This is not a Grasshopper workshop. We're just going to try to introduce how these tools are used from the perspective of biodesign to try to get you interested in these tools. For most of these things, you can find a lot of resources online. If at any point, I'm not really good at Houdini, but I think I'm okay at Grasshopper. So if at any point you have a question on Grasshopper, you can send me an email. I honestly enjoy solving problems in Grasshopper, so it won't bother me. It's fine. There's also tutorials online on Houdini. You can CFD is a bit tricky to find tutorials, but you can still find them. So yeah, we're just trying to get you guys interested in using these tools and showing you how to use them from the perspective of biodesign, so you guys can continue learning on your own. And yeah, whenever you want to send us an email to ask something, I guess this is also about building a community, right? Okay, guys, so if anybody wants to show anything else, we can do it in like 5 minutes, because I have to go to work. It's the morning for me, and I said that I was gonna be there sometime in the afternoon. So yeah, if anybody wants to show us anything, we can do it super quickly. Otherwise, we can wrap it up, and we can see you tomorrow to discuss the computational tools that we want to introduce to you guys. Okay, then I guess we're good for the day. This has been super fun, guys. We're gonna post the recording in the YouTube playlist. I sent you guys the list of software that we need in the brief. I'm gonna put it in the I'm gonna send the brief document again. As Dan is saying, no, it's not Adobe CFD, it's Autodesk CFD. Autodesk CFD, which you can get a trial version for, Houdini Apprentice, which is free. I hope that you guys have Rhino. Rhino is not free, but you can also get a trial version. Yes, we are gonna, as soon as we get the recording down, we're gonna post it on YouTube in the playlist that Digital Futures shared with you guys. It's gonna be posted as day one. Yeah, super fun, guys. Really looking forward to tomorrow. I'm gonna resend the brief to all of your emails. The list of programs is in the brief, as well as a couple of links on how to install Grasshopper plugins and everything. Any questions, send us an email, and we'll see you guys tomorrow.
All right. Thanks, guys.
Thank you, guys.